Alright, we're going to look at a couple practice problems to get ready for our quiz for Module 2. This first question says, does the graph of f of x equal 2x cubed minus x plus 3 have symmetry with the x-axis, y-axis, origin, or none of these? So we could go through the algebraic proof of this, but what I did is I just went ahead and graphed it. And since this is the y-axis, it certainly does not split over there. If I flip it, it's not the same. Definitely has no symmetry with the x-axis, because if I flip it over there, it doesn't become the same. So let's look at this origin. Now if I flip it over the origin, it's going to be somewhere down here. Remember, we could take a point. Let's look at this point. It looks something like 1/2, comma, I don't know, 3.5. So if that's true, then we would know the point down here for symmetric to the origin would have to be negative 3.5, negative half. And that point just isn't on the graph. So this is not really symmetric to any of them, so this has no symmetry with those three choices. Question 2 talks about even or odd functions. Now, the formal definition of even odd, if we recall, an even function, a function was even if f of negative x equals f of x. And it was odd if f of negative x equals negative f of x. We also said even functions have symmetry with the y-axis and odd functions have symmetry with the origin. So if I look at this graph, you can kind of clearly see that it definitely has symmetry with the origin, or excuse me, the y-axis. So because it's equal on both sides of this axis. So I'm thinking it's an even function. To check this, what I can do is I can plug in negative x. So everywhere I see x, I'll put in negative x, and we'll see if we get back to the original function. If we do, it is definitely even. So you have the graphical geometric check, and then you have the algebraic check. Both are very efficient. So negative x squared is x squared plus 4, which is right back to the original function g of x, because negative x squared is just positive x squared. So this is an even function. Let's look at the second function, a little more complicated. X over x squared minus 1. So looking at the graph, it is certainly not even, because it's not symmetric to the y-axis, but it appears to have a symmetry to the origin. So if either of them, I would think it's odd. So let's just go ahead and verify that it is odd by plugging in negative x and see if we get the opposite of the function. So I plug in negative x to the top, I plug in negative x to the bottom, everywhere there's an x. So I'm plugging in the h of negative x. So this h of negative x is going to leave me with negative x over x squared minus 1. Same idea, that becomes positive on the bottom. Well, now if I just factor that negative x out on the top, because there's just one left, I could rewrite this whole thing as negative x over x squared minus 1. So now it is the exact opposite of h of x. So since it's the exact opposite of h of x, we call this an odd function. So it's odd not only because it equals this negative function, but it's also symmetric to the origin. So if I flip this graph over, you know, this curved part would match up with this curved part, and this part would match up with this part. Alright, so a couple questions on transformations. What transformations occur from the parent function to x minus 3 plus 1? Well, we should always start on the inside, so I would start with this x minus 3. So any adding and subtracting on the inside is going to be a horizontal shift, the opposite direction of the sign. So in this case it is minus 3, so that's going to cause a shift to the right of 3. The next one I would do, by our PEMDAS, you do the parentheses, then I would do exponents, which there are none. Then I would do the multiplication, which is this 2. So a 2 multiplied to the front, that's a vertical dilation. It's a bigger number, so in this case that would be a vertical stretch. Remember, if that number was negative, it would also do a vertical reflection. In this case, it's not. And our last one is that plus 1 at the end, which is, of course, a shift up 1. Now, I didn't graph this, but you could, of course, graph this just to make sure that it verifies to give you the same thing, just to help you. All right, let's look at another problem very similar. So we have what transformations occur from the parent function. So the parent function is, of course, a squaring function. So I see first inside x minus 1, so that's going to give us a shift right 1. Again, opposite sign. Then I see two negative signs. So the negative side inside, remember that is a horizontal reflection. The negative just flips it, and a horizontal reflection means it's going to flip over the y-axis. So we would flip that whole thing over the y-axis. And then we have this other negative on the outside. Whoops, this one here. Right here. That negative is on the outside, and that's a vertical reflection. Remember, everything that happens on the inside of the function is horizontal stuff, and anything that happens on the outside is going to be vertical stuff. So this one had two reflections, both a horizontal and a vertical, and also one of the shifts to the right. Okay, let's look and see if we can't write a function when we have a graph. Based on the transformations below, what is the equation of the graph below? Well, first I'd go back to my 1, 2, and I'd recognize that this looks like a cubic function. So this is some kind of y equals x cubed function, and then it's got to figure out what transformations have occurred. So a cube will typically look like this. So the middle part's typically at 0, 0, where now I see this middle part is over here. So I think that we've gone left 2, and we've gone down 2. The other thing I see is that instead of going from the bottom left to the top right, it goes from the top left to the bottom right. So I think it's been reflected, so I think it has a vertical reflection. So if I want to write this function with the transformations, y equals, now I'll first do the shift left 2, which I know is x plus 2 cubed. Make sure it's plus because it's going to the left. I'm going to put the minus 2 out here for the shift down, and then the vertical reflect, I'll put the negative outside. And this is a really easy one to check because I could just graph this and make sure it matches what this graph looks like. And it'll match very well. Okay, our last example comes from our last kind of section where we were doing increasing, decreasing, constant. So we want to know what are the intervals of increasing, decreasing, or constant for the function. Also stating local maxes or mins. So if I look at this graph, I graph this on Desmos obviously. I can see the graph is going down until it gets to this point. And then it goes up for just a little bit, right? So this is definitely a local min. It's going from decreasing to increasing. And then I get to this point, which is going to be a local max. And then it's going to start decreasing again. And it's going to decrease all the way down to this bottom point, where this has to, of course, be a local min. So we have two local mins and a local max on this graph. And then it will start increasing again. And it's going to increase forever. Now we've got to be very careful when we write our intervals for this, because remember, the intervals only use the x value. So when I do my increasing intervals, and my decreasing intervals, I'm going to only use the x value. So I'll start with the decreasing, because this function was decreasing forever. So it's decreasing from negative infinity, the x value, because it's going down, so the x's are, for every negative x value, it's basically going down, until I get to that x value, negative 0.392. And then it's going to increase for just a little bit. But then I'll union that, and the second part of decreasing is this second part here. And that decreases from 0.429 all the way down to that bottom point, which is 4.462. So those are my decreasing intervals. And then, of course, my increasing intervals, I got just this little guy right there that's not increasing for very long. But it is increasing, so that's negative 0.392, comma 0.429, union. And then the last part is that big part, which is going to be 4.462, comma infinity. So the biggest thing I can tell you for this, when you're writing it, make sure you're only using the x values. Beyond that, not too tough a thing to do. Hopefully this was valuable for you. If you have any questions before the quiz, of course, please let me know.